Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. In the previous lecture we have seen how we can relate the different performance metrics of a second order system with respect to the pole locations, and if you see on your screen right now you will see that we have actually marked out this portion in red to specify all such possible poles which would give rise to percentage overshoot less than a certain value, settling time less than a certain value, and also rise time less than a certain value, which is to say that if your poles, so I am drawing it in green now here, if your poles are to the left of this region that I have marked in green here, which is the hatched portion in red, then you are guaranteed that the percentage overshoot, the settling time and the rise time specifications that your system is required to meet will actually be met. Now that we have seen this, it's about time that we actually investigated a little deeper. So say for instance, now suppose someone gives you a couple of systems, both second order let's say, and they specify to you the pole locations, right. Now with respect to these performance metrics that we've studied, we should be able to compare between these two systems, because you know we've already seen that just by understanding the location of the poles, we would be in a position to determine at least qualitatively, if not quantitatively, as to which one has a higher settling time, which one has a higher percentage overshoot, which one has a higher rise time, and so on and so forth. So pushing ourselves a little towards that direction, we will now study the following cases. These are some particular cases that are also covered in most standard textbooks, but that shouldn't tell you that these are the only kinds of comparisons that we can make. There can be several different types of comparisons. Any two arbitrary second order systems, given that their pole locations are specified, should be comparable by these performance metrics. Okay? So at least now you know that given two dynamical systems, and someone asks you which is a better system, without qualifying that statement better, having understood these performance metrics, you would be immediately able to relate to what that meaning of the term better system implies. Okay. All right. So now suppose you have, let's say, two systems both having, and when I say system, by default I mean here second order systems. Okay. So suppose both of these systems, underdamped second order systems, have exactly the same damping ratio. Okay. So as you know, the complex poles appear in conjugate pairs. So now you are asked to compare between the time domain responses, at least qualitatively, the time domain responses of the system whose poles are marked in blue and those of the system whose poles are marked in green. And how do you go about this business? So okay, let's see, this is the time axis, this is let's say the step response, the output axis. So what can we say about these two? First, notice that the real parts of the poles marked in blue are smaller than the real parts of the poles marked in green, which immediately tells you that the settling time for the system marked with blue poles, the settling time will be higher. In other words, it will be a more sluggish system. We also know this intuitively by the fact that the closer the poles are to the imaginary axis, the slower is the rate of decay, and consequently the slower is the response of the system, right. So now what else can we say about this? You see that these are both poles that lie on the constant zeta line. So what do we know about the constant zeta line? We know that the percentage overshoot of the system is exclusively a function of the zeta. So if you keep zeta constant, the percentage overshoot of both these systems marked in blue and green should be identical. So what comes hand in hand with the percentage overshoot? Well, you have here, let's say this is your steady state value, and let's say arbitrarily, that's why I said it's qualitative, we are not really computing the exact value of this phi, right? If you knew this, you would know exactly the value, the quantitative value of the percentage overshoot, but let's say this is some arbitrary value of percentage overshoot corresponding to this particular phi, right? So you see that both the blue and the green systems, right, should have the same peak value, same percentage overshoot. Now the next question is, which one attains this percentage overshoot value sooner than the other? Again, the answer is to be had from the fact that, by observing the fact that, you see the peak time is exclusively a function of the imaginary part of the pole, right? The larger the imaginary part of the pole, the sooner is the peak attained. In this case, we see clearly the green system will have a larger imaginary part, and therefore, imaginary part of the pole, that is. So therefore, you see, just by looking at the pole locations, you can compare between these two systems and say that the green system will attain its peak sooner. Okay? If that is the green system, of course the blue system should also attain the same value of peak by virtue of the fact that they both share the same value of zeta, right? But then suppose the blue system will probably attain its peak later, all right, because the imaginary part is smaller. So if I am to draw the blue system here, that is probably what the step response of the blue system is going to look like. What else can I say from this? Of course, you see that you can talk about the envelopes of these two systems. What is the envelope dependent on? You know, the envelope governs the settling time, and we've already discussed that the settling time of the green system must be lesser than the settling time of the blue system. In other words, the blue system is more sluggish, right? So therefore, you see that the green system's envelope must decay sooner, all right? So the green system's envelope must decay sooner. In other words, if you want to draw the envelope, this is how the envelope of the green system would look like, something like this, and the blue system's envelope would be slower, right? So you see, a lot of these things can be inferred just by qualitatively looking at the relative locations of the two poles, okay? So that is the first observation we make about this, all right? What about the scenario, let's say, when you have two poles or two pairs of poles having the same settling time, which is to say the same real part of the pole. Now immediately, as we've discussed in the previous case, you'll see that they share the same envelope, all right? So the envelope of the two functions is going to be the same, all right? So that's a common envelope that they share, yeah? Right. But what about the remaining parameters? You see, once again, the green fellow has a larger imaginary part. In other words, the green fellow will attain its peak sooner, okay? The other thing that comes hand in hand with this, if you now draw lines joining the green fellow and the blue fellow to the origin, you'll immediately see that the phi 1 corresponding to the green fellow is smaller than the phi 2 corresponding to the blue fellow, which means that the blue fellow, the blue system, is more heavily damped, which would obviously then lead to what? We've already seen in this figure, right? So the more the damping, the lesser the percentage overshoot. And you see that fits in very nicely with the picture, because now the blue fellow has lesser percentage overshoot and the blue fellow also attains its peak later. So if I draw the blue step response here, it would look something like this, and if I draw the green response here, it would obviously attain a higher percentage overshoot because of the lighter damping, and it would also attain its peak sooner. So therefore, this is in all probability what the response of the green system is going to be like, right? Right. The other thing to notice here is, of course, the fact that what happens to the imaginary part. You see, the larger the imaginary part, the higher the frequency. So you see, within a given span of time, the number of peaks and troughs of the green fellow is going to be greater than the number of peaks and troughs of the blue fellow, because the frequency, you remember, which was omega n times square root of 1 minus zeta squared. The smaller your phi, the smaller your zeta, therefore the larger the value of 1 minus zeta squared, the larger the value of its square root, and the larger the value of this damped frequency. So the higher the damped frequency, the more the number of peaks and troughs in a given time interval. Alright, so we can also deduce the same thing from here in the preceding diagram, this preceding figure which we had considered. You see, I have deliberately drawn this green fellow to be more oscillatory in nature, or to have a higher frequency of oscillations, for the same reason, because the imaginary part of the green fellow is larger, so therefore it will have higher frequency of oscillations. Okay, so notice the beautiful thing about all of this is that we are not even getting into any quantitative comparison of sorts. Just by looking at the relative locations of the poles, we are able to infer about all of these things. Okay, to just complete the picture in its entirety, we will now draw the final case where we have, so let me just mark this is R, this is JR, this is R, this is JR. So again, this is R, the real axis, and this is the imaginary axis. Right. Now once again, suppose now we have the two pairs of poles given by this blue and green locations for the two systems. Okay, so the blue one is system 1, the green one is system 2. What can we say about these? Right. So once again, if you are trying to compare qualitatively, what happens here? Once again, you see this time the green and the blue system, both of them have the same imaginary part of the poles, which means that their peak times will be the same, that is, the peaks will be attained at the same time. But the question then obviously is, which one has a higher peak? There are a couple of ways actually to answer this question. First, you notice that again the green fellow is this time more heavily damped than the blue fellow. Alright, so this then clearly tells you that the higher the damping, the lesser is the percentage overshoot. Alright, so if they are both attaining their peaks at the same time, right, if they both attain their peaks, let's say at some time instant here, this is, let's say, the TP, and one of them has a higher percentage overshoot than the other, the blue one will have a higher percentage overshoot. Why? Because it is lightly damped. So here, if I draw the blue one here like this, right, then the green one, which will also attain its peak at exactly the same instant, will have a lower percentage overshoot. What about the other aspect? You see, they both have the same frequency of oscillation, so their peaks and troughs would all coincide. Okay, not just the first peak and the first trough and so on, but all of their peaks and troughs would coincide. But you see, the important thing to notice here is that the green fellow is more heavily damped, and also the settling time of the green fellow is lower, because the real part of the green poles are higher or larger. So therefore, if you draw the relative envelopes, you would see that the envelope of the green fellow will decay way sooner than the envelope of the blue fellow. Okay, so there are multiple ways of inferring all of this. Okay, so if you just want to answer the question as to which one has a higher settling time, which one has a higher percentage overshoot, which one has a higher rise time, and which one has a higher other such metrics like let's say damping ratio and so on, right, you can always infer about it just by looking at the relative locations of the poles, right. So that is an interesting bit. Okay, so now having seen all of this, it seems like we have covered a lot of ground, and that we are well on our way to understanding the responses of systems, the behaviors of systems, which are subjected to a step input, right. But remember, we would do well to remember at this point that we have only studied second order systems. How good are these? Okay. Is it really good enough to just study second order systems to understand about the general behavior of the systems? Can every other system be approximated by a second order system? It turns out that unfortunately that is not the case. So under what circumstances is all of this analysis or this study that we have carried out actually going to be useful? We should like to draw the boundary around it and say that, okay, so we have understood a class of systems such and such which have such and such property, but if they do not have these properties, then all of this analysis that we have carried out might not be as helpful or useful to us. Okay, right. So in order to understand that, we now extend our study to cover systems which have, let's say, so in general a system can have n poles and m zeros where n is greater than or equal to m, because we are only considering strictly proper or biproper systems which are physically realizable, right. So n does not necessarily have to be 2, but we have so far focused our attention only on 2. The reason being that we will now study the general system as an addendum to this second order system. In what sense? We will say that, okay, we will have 2 so called dominant poles, and the remaining poles, and if there are zeros, then those poles and zeros will be considered as added effects, like extras in a shooting crew for a movie. Okay, and we will see whether these extras actually turn out to be the central characters in the drama eventually. Okay, and when they do turn out to be so, right. So that is the question before us. So let us consider the following as the next topic of our investigation, which is effects of additional poles and zeros. All right. Okay. So let us consider one at a time. Let us not get ahead of ourselves and consider the general case here. So suppose you have one additional 0 to a second order system. Since we do not want to alter the DC gain, we would consider the structure of the 0 to be thus. You see that now if you plug in S is equal to 0, the DC gain of the system does not alter. We already discussed what the DC gain of the system is in the preceding lecture, so that part should be obvious. Okay. Suppose tau is greater than 0, we will later on also consider the possibility when tau is negative. Okay, so that is an additional 0. What if we also have, let us say, systems of the form omega n squared upon s squared plus 2 zeta omega n s plus omega n squared times 1 plus s tau. Once again, we are not tampering with the DC gain. In this case, of course, we will always consider only tau greater than 0. So remember, in the former case, also consider tau less than 0. Okay, but in this case, we will not consider tau less than 0, because that would be tantamount to an unstable system whose behavior we are really not interested in studying, at least not as of now. Okay, so now our object of study or interest would be transfer functions of this nature, and it turns out, now you will have to take my word for it, it is a kind of like a rule of thumb. We will see later on. Of course, you can also convince yourself and derive this, but for now we will say that if minus 1 by tau is comparable to minus zeta omega n, then all the performance metrics we have derived, all the expressions for the performance metrics of course remain the same, but the expressions for the performance metrics we have derived cease to be effective. So we must warn ourselves, this is a very important point. You might derive all these performance metrics as we have done for second order systems, but the moment you have additional poles and zeros, you cannot just blindly say, okay, we still have the same expression, like for instance, settling time is given by 4 by zeta omega n. No, it wouldn't necessarily be that, right? because this additional pole and 0 definitely has some added dynamics to the system. If I look at it from the time domain perspective, it's a higher order differential equation in the first place, right. So it would be kind of wishful thinking to expect those same expressions to be valid irrespective of the value of this additional parameter, which is tau, which could be a pole or could be a 0, right. So that is a rule we will kind of respect. The reason being, let's just get a qualitative understanding of this. Again, I'm not going to, you can convince yourself with some numerical values about the validity of what I'm claiming now. Now let's say, for instance, you have, you want to find out the step response of G1s, right, and you want to find out the step response of G2s, right, you want to find out this, right, and based on this you want to find out what your peak value is, percentage overshoot is, peak time is, rise time is, settling time is, so on and so forth, all right. Now you have to account for this added parameter, which is this added pole or 0. So how do we generally expand? If you recall, we would normally expand this first one as again the same A by S plus B S plus C upon S square plus 2 zeta omega n S plus omega n squared plus D upon okay, S plus 1 by tau, alright. So now notice that everything else, the form of this expression remains the same except for this new parameter. Oh, is it, okay, let me just change the order. This is G2 by the way, which is the additional pole. Of course the 0 will not have any added mode. So let's say this is the pole. So, and let's just flip the order. I just made a mistake. I just considered the 0 and I was considering the pole on the right hand side. So okay, so for G2 you will have this added parameter here. So notice that now apart from the usual terms which appeared for the second order system, you have this additional mode. So if you now apply the Laplace inverse on each of these terms individually, right, what is the Laplace inverse of this term going to be like? It's going to be something like d e to the power minus t by tau, right. So in the time domain, if you want to ignore the effect of this term, there are two ways in which you could do that. One, suppose tau is very small. What does that mean? If tau is very small, it means that this exponential mode is very fast, or 1 by tau is very large, which means that the third pole, that is 1 by tau minus 1 by tau, is far away from the imaginary axis. Okay, so definitely it will then not satisfy this condition. Okay, if it's very far away, then what happens? The effect of this third mode decays very soon. It's like there is a time scale separation between the responses due to the remaining modes, which is one of course due to the input, the other due to the system's second order modes, and the third due to this additional pole, alright. So one, of course, if tau is very small, right, then you have this fact that this will decay very soon, so the effect is hardly perceptible in the long run. So most of the performance metrics whose expressions we've derived would possibly continue to hold good. The other fact is that notice if tau is very small, or if minus 1 by tau is very far from the imaginary axis on the left half plane, what happens when you try to evaluate d? After all, this d is obtained by evaluating the residue. If you recall how we obtained our inverse Laplace transforms, you see, how do you obtain d? You multiply both sides by s plus 1 by tau, right? So you multiply both sides of that expression, which is basically nothing but this. You multiply this by 1 plus s tau, alright, or s plus 1 by tau, whichever way it suits you. You multiply it on both sides, and then you try and evaluate the value of this entire expression, which will then be the remaining terms at s is equal to minus 1 by tau. Now if you do that, you will see that because of the value of tau being very small, yeah, and I leave that to you as an exercise to check that this value of d, yeah, so you will have two consequences, e to the power minus t by tau decays soon, which we have already established, and the second consequence which I am claiming is, if you just do an analysis, not really a very deep analysis, but if you just try to do this residue analysis, right, find out the value of d when 1 by tau is much, so suppose what I am saying essentially is that tau is very small. Another way of stating that is 1 by tau magnitude is much greater than zeta omega n, sorry, which is the real part of the underdamped poles, right. Of course, zeta omega n is anyway positive, but just we are putting this modulus sign, absolute value. You could also omit this, but does not matter. So the point is, when tau is very small, then this is what is going to be true, and if this is true, then I urge you to check through an analysis of this residue that the second thing that happens is d is small. So you see, there are both benefits, two ways there are, it is benefiting you if your poles are far to the left half plane. One, the mode as it is hardly has effect on the system's response beyond a certain time instant, right. If tau is very small, then beyond the first time constant, which is tau seconds, right. So for instance, if your zeta omega n is, let us say, in milliseconds, and if your tau is in microseconds, right, then within 5 microseconds, for instance, this mode has already decayed and ceased to have any significant effect on the overall response. So for all practical purposes, you can approximate the system as a second order. The second thing that happens is, of course, if the d is also in addition small, which will be the case, because as I am claiming now, if you do this residue analysis, you will figure that this d is going to be small, right. You check that out, you will have a tau squared sitting in the top of the expression for d, right, and because as you make tau smaller and smaller, this expression gets smaller, this expression d gets smaller as well. The point is that as d gets smaller, even if, for instance, this mode hadn't decayed very fast, after all, this is only going to contribute very little to the overall weighted response of this system, isn't it? So therefore, there are two benefits to this. If your pole, your additional pole is far to the left half, you can safely ignore it, yeah. So that is the sort of thumb rule. What happens with the 0 is a little more interesting in the sense that, we haven't really studied the effect of 0 with respect to these Laplace transforms and their inverses. So let us see what happens with the 0. One thing we know about the 0 though is that the effect of an additional 0 is like adding the derivative of a certain term to itself. Why do I say that? So suppose you have y plus y dot, you want to find out the Laplace transform of this is going to be nothing but ys plus s times ys. That is going to be nothing but s plus 1 times ys. So you see, this is nothing but an additional 0. So the way to view, I am putting it to you, that the way to view the effect of an additional 0 is to consider that you have the normal response of the system, the second order response, and to it you add the derivative of that same response and see the effect overall. And that should be able to tell you as to in what way the 0 affects the step response of the system with the additional 0, how it changes with the addition of this extra 0. Okay. So let us take a look at this, and yeah. So suppose, okay, so we finished this, yeah. So suppose you have, as I said, tau greater than 0, and you consider G1s 1 by s times Laplace inverse. So this is going to be nothing but like the Laplace inverse of 1 by s Gs, right. So plus the Laplace inverse of 1 by s into s tau times Gs, where Gs is basically this pristine second order system. Okay, let me just mark it out. Yeah, without this. So this is what I am deciding to call as GS, right. So now you see immediately what follows is that this S and S will cancel. So this is going to be the usual response that we understand, alright. So this, of course, we know what this looks like. This is going to be the usual YT plus, what is this? This is going to be tau times Y dashed or Y dot, whatever you choose, T. So you see, the smaller the value of this tau, the lesser is the effect of the 0. What does that mean? If the smaller is the value of this tau, once again you see if tau is very small, we saw what the effect was on the additional pole. Now also you see that if you make tau very small, then the effect of the 0 is also very small. So for smaller tau values we do not really care much. What happens if tau increases? The more you increase tau, the more the weight increases on the derivative. So let us quickly have a qualitative sketch of this step response, okay, plus tau times Y dashed t. So let me first draw the usual step response that we have seen so often now, okay, that is Y tau, YT, sorry, right. Now what about the derivative? Notice that until the first peak is attained, the step response is only rising. So therefore we know that during this interval Y dashed is positive. As the first peak is attained, of course Y dashed is 0, right. Then until the second maxima or extrema, not maxima, the second extrema, which is a trough, here you see the derivative being negative, alright. So my drawing is bad, so therefore it looks like these intervals are not equal, but trust me, these intervals are equal, okay. So now you see, based on this you can draw tau times, so I am scaling it up by tau. So let us say for some given value of tau which corresponds to a 0 location, this is what gets superposed, right. So what does this do? Now if you want to cook up the net assembly, if you want to cook up the net effect of the 0, you see during this interval it gets added, so it adds more to this, right. So therefore this is the overall effect, this is Y plus tau Y dashed. Notice that at the peaks and the troughs the curves will intersect. Why? Because at those points Y dashed is equal to 0. So it is as if the effect of the 0 is not to be seen at the original peaks and troughs of the natural second order system, okay. Right. So this is how, again a very rough sketch and probably a not very satisfactory one, but this is how you see that the effect of the 0, an additional 0 on the left half plane, has the effect of moving the system response to the left. So it prepones, or that is Indian English, so it kind of brings the peak time forward, it increases the percentage overshoot, right. So these are the general effects. So it decreases the rise time, increases the percentage overshoot, yeah, decreases the peak time, right, and possibly also increases the settling time, alright. Maybe not much effect on the settling time though, because settling time is after steady state is reached, when basically the fluctuations of Y are not much, so the derivatives of Y will be smaller. So maybe as you get closer and closer to the steady state, the effect of the 0 is not felt anymore, yeah, because this is like kind of telling you how soon, at what rate the response is changing. So you see the original response to the second order system does not fluctuate much as you near the steady state. So of course the effect of Y dashed is also hardly perceptible at those, for higher values of time, yeah, as t increases, even if tau might be considerably a large value, okay. So now that we have seen this, why only restrict ourselves to positive values of tau? So let us look at what will happen. We are in a very good position to study what will happen if you have negative values of tau. So again we draw this natural response due to the second order system, but now because we have tau is negative here, you see that now if I split it up like this between the peaks and the troughs and so on and so forth, right. Now you see that between this 0th instant, that is t is equal to 0, and the peak time, you will have a negative value of this term. Why? Because tau itself is negative. So therefore this is what will happen. Nothing happens to the original response, only the part that has to do with the 0 gets flipped, its sign gets flipped. So now if you want to draw the overall response of the system, you see that at this point y dash is equal to 0. So the overall response of the system then becomes something like, first starts with like an undershoot of sorts, okay, starts with sort of an undershoot and then has this, of course, probably not a very correct picture, because as I said, at the peaks and the troughs it should coincide with the graph, with the original plot. So probably it gets a delayed peak, slightly higher peak than the original one. It's getting tricky for me to draw here, but I hope you get the idea as to, I'm a little finicky about this because I want these to meet, right. So you see that the effect of a 0 on the right hand side is in effect to have the system shifted to the right a bit, okay. That's like, it's like delaying the response of the system a bit. So your rise time increases, your peak time increases, peak overshoot of course also still increases, but notice that what happens now is that you see that you can easily correlate that. It's a short way to remember, a shortcut to remember, that if your tau is on the, if your tau is like positive, which is to say that the 0 is on the left half plane, it has the effect of shifting the step response to the left. If your tau is negative, which is to say that the 0 is on the right half plane, it has the effect of shifting the step response to the right. Now also this is one of the reasons why you see a pure delay term like e to the minus s t, something like this, yeah, is often approximated. So these are called something called Padé approximations, which we will probably visit at some point in time if we have time. No promises there. So this is a Padé approximation. There are different orders of Padé approximation. So a first order Padé approximation of this pure delay term, not surprisingly, consists of something like this. Okay, this is like, of course this is not exactly equal, this is a first order approximation of Padé approximation. So you see, not surprisingly, this has a right half plane, of course this t is assumed to be positive, so this has a right half plane 0, right, and we see that whenever you have a right half plane 0, you have this sort of an undershoot. We saw this as a matter of fact even with the first order step response, if you recall, right. So that is an important thing. So to finally conclude our discussions on these effects of additional poles and zeros, let us quickly summarize it in this particular, in the form of this particular picture to leave you with, all right. So if you are given, for example, a number of such plots, something like this, and then you have something like this, yeah, and then let us say you have another one, something like this, and you have something like this, yeah. Even though I am not very aesthetically gifted, I am still happy with the consequence of this drawing, where you see that excuse me, where you see that at the peak of the original second order system, this is response without any 0, Alright. So you see that at the peaks and troughs of this, every other response, whether with or without a pole on 0 on the right half or the left half plane, they will intersect. Okay. So these are critical points, as we have already discussed. Why? Because at the peaks and troughs the derivatives would vanish. So if someone gives you a figure like this and asks you to compare between the relative locations of the poles and zeros for these figures, you should be able to immediately tell that the green response comes from a system which we term as something called a non-minimum. Again, why we are using this term will be clear later when we do frequency responses. So this comes from the so called non-minimum phase system, which means a 0 in the right half plane. Alright, and as you can see here, the red one of course and the blue one along with it, both of them come from systems with zeros on the left half plane, but which one has a larger value of the tau? Clearly the blue one. So larger value of tau means 1 by tau is smaller, right? So what does 1 by tau being smaller mean? Yeah, 1 by tau being smaller means it's closer to the imaginary axis. So the farther your pole is from the imaginary axis, yeah, 1 by tau magnitude tends to get larger, and 1 by tau gets larger means tau gets smaller. Yeah, so tau gets smaller means you see that your system response with the 0 comes closer and closer to the original response without any zeros. Okay, the aberrations from the system without any 0 get larger and larger as your tau value increases. Not surprising at all in view of the discussions we have had so far. Okay, so the take home message therefore from all of this discussion is, with zeros, well, it's all well and good, you understand what happens when there are zeros on the right half plane, when there are zeros on the left half plane, right? But with poles we have certain strict rules where we can and cannot approximate a higher order system by a second order system. Unfortunately, if that rule of thumb is not met, or it's violated rather, that 1 by tau magnitude wise is closer to zeta omega n, then all of these approximation techniques will not hold good anymore. So just to summarize that, suppose you have a pair of poles like this. So of course you know that this is minus zeta omega n, right? If your third pole is somewhere here, and we say that this is almost like 5 times zeta omega n or more, right, or more to the left, yeah, then we can ignore this. So that's a good rule of thumb. Then we can ignore this pole. Alright, so we say that these fellows are then the dominant poles, the ones that are closer to the imaginary axis, they are dominant poles. So the dominant poles govern the overall response of the system more or less, and we can ignore the additional pole. Alright, so that is one way of seeing this. Of course there is no guarantee that the additional pole is always going to be complex. So for example, if you have over damped systems or critically damped systems where there are repeated poles, then you have obviously have, let's say, 2 poles which are closer to the imaginary axis and let's say a third pole which is farther. In that case, the rule that we generally employ is, out of the 2 poles that are closer to the imaginary axis, take the one that is farther, let's say this one, call this sigma, and if this distance is 5 sigma or more, then you can ignore the effect of this. Then you can ignore the effect of this. Alright. There is another way by which, even if this 5 sigma rule is not met, you are often able to ignore. But remember, all of these discussions that we are having, these are all qualitative, and strictly speaking, you should never accept these at face value. Let's say when there are many more poles and zeros, you should never accept these at face value. You should always run a simulation. Remember, in our very first lecture, we said that although for your exam purposes or for the purpose of this course mostly, you shall only consider the analytical aspects. But remember, any control system design is never complete, or even the analysis is never complete until you have carried out some simulations, okay, to to validate your understanding of the system. Okay, so even if this 5 sigma rule, so called 5 sigma rule that I am naming it or christening it, is not met, you might still sometimes be able to ignore additional poles and zeros. When is that possible? Recall, here there are two factors that are allowing us to ignore the effects of the additional mode. One, the fact that this exponential term decays very soon. Okay, the moment you don't have that 5 sigma condition, this will no longer be true. In other words, if this 1 by tau is not fast enough, okay, if tau is not small enough or 1 by tau is not large enough, then this e to the minus t by tau will not decay soon enough for your liking. In that case, what hope can you have? The hope is that suppose this d is small, but again we have seen here in this case that there is no way that the d is going to be small, because d is after all kind of proportional to tau. Yeah. So if you make your tau small in one shot, the decay term will also decay sooner, this decaying exponential, and the value of d, the weight associated with that decaying exponential, also goes down. But can there be a situation where the decay term may not be very fast decaying, or that exponential may not decay very fast, but the value of d, okay, the residue is still small? In such a case, maybe we will still be able to ignore the effect of this extra mode or this added pole, even though it does not decay soon enough. Sounds like, counterintuitive, isn't it? But I assure you that such things do happen, and again you can convince yourself, it's just a very simple exercise. So suppose you have this omega n squared upon s squared plus 2 zeta omega n s plus omega n squared, and then you have 1 plus s tau z upon 1 plus s tau p. Alright, and now tau p and tau z do not satisfy this, okay, it's my given name, okay, don't go about in the textbooks looking for this so called 5 sigma rule, okay, I am calling it a 5 sigma rule, don't look for this in a standard textbook. So it's so suppose it does not satisfy this 5 sigma rule, which is to say that, now suppose you have these couple of poles here, and the third pole and the 0, both of them are within this 5 sigma. So this is, let's say, sigma, and this is 5 sigma. So instead of being on the left of this 5 sigma line, both of them are, let's say, the added pole and 0 are, let's say, somewhere here. Then under such circumstances, can we still be able to approximate this system, which is clearly a third order system with an additional 0, can we still approximate this as this typical second order system? Right? Can we do that? The answer is thankfully yes, but we have to understand when can we do that. When we can do that is this situation, where if tau z is very close to tau p, remember, so if tau z is very close to tau p, what does that mean? It's essentially as if the pole and the 0 are cancelling out each other. That is one way of seeing why this sort of an approximation might work. The other way to see this is, now if you want to find out the step response of this system, so let's say 1 by s GA of s, and again I will leave this to you as an exercise to convince yourself that this will have, let's say, again a term like a by s plus b by s squared, bs plus c, that is, by s squared plus 2 zeta omega n s plus omega n squared plus d upon s plus 1 by tau p. Now in this case, you see what will happen is, when you take the Laplace inverse of these individual terms, you see the Laplace inverse of this particular term comes out to be again d e to the power minus t by tau p, but because now this tau z is almost equal to tau p or very close to tau p, you will have this contrary situation where even though this exponential does not decay soon enough. Why does the exponential not decay soon enough? Because tau p is clearly not small enough. Okay, so because tau p is not small enough, in magnitude, the exponential does not decay soon enough. However, again you carry out the residue analysis, you will see, unlike in the other case, here you will see this d has a small value if tau p minus tau z tends to 0. So you can try out different values, let us say you give this some small value epsilon 1, epsilon 2, and you can keep changing. So it is an interesting exercise, okay. You can just try this as an exercise, checking the value of this residue. So first you take, let us say, tau p into 1 plus epsilon is equal to tau z, and try with small values of epsilon, say epsilon is equal to epsilon 1, epsilon 2, so on, okay, etc. So this is an exercise, and you see that as you keep making this epsilon smaller and smaller, this value of d decreases. So even though this third mode, this additional mode due to this extra pole may not decay soon enough, alright, because of this residue being small, its effect is hardly perceptible, okay, it is almost negligible is what we say. So in such cases, even if this 5 sigma rule is not satisfied, you might still be able to approximate this sort of a system as a second order system. Okay, so that provides us with enough incentives to study for these performance metrics of second order systems. Okay, so with that being said, let me warn you of another thing here, right. The other fact to be remembered here is that notice that all the things that we have studied here, we have not mentioned about whether these are open loop systems or closed loop systems. Okay, so for example, if you have say Gs given by some A upon S into S plus B, okay, right. Apparently this has nothing to do with the system we have studied so far. Of course it has, I mean you can always say that this is an sort of an overdamped system with two distinct poles at 0 and minus B, okay, but that is not why I have taken up this system. You see, where we will be most interested in is when we put this Gs here, alright, and then we close a loop around it. So there are several reasons why we go for feedback, why we go for a closed loop configuration, as we have discussed in the very first lecture if you recall, okay. So let us say this is Rs and this is Ys. So now notice that if you want to get to the heart of this problem of finding out the transfer function from R to Y, what do? You call this variable as, let us say, E of S. So therefore you see Y of S is equal to G of S times E of S, and what is E of S? E of S is nothing but your reference input minus your Y. So now if we substitute this, so this is equation 1, this is equation 2, if you substitute this you will get Y of S is equal to G of S times R of S minus Y of S. So therefore we get that Y of S times 1 plus G of S is equal to G of S times R of S, which is nothing but Y of S upon R of S, which is our desired closed loop transfer function. So this is basically the open loop transfer function, and now if you want to find out the closed loop transfer function, which is the equivalent transfer function of this block that I have put in a dotted or dashed box, is going to be nothing but G of S upon 1 plus G of S. Now notice, what is this G of S upon 1 plus GS? If you plug in everything here, you will see that this is nothing but S plus B upon 1 plus A times S into S plus B is equal to G closed loop transfer function. Okay. So what is G CL TF? If I simplify this term further, I will get this as A over S squared plus BS plus A. Okay. This now is comparable to the system that we have studied. So why did I bring in this closed loop? Because for the remainder of our course, for most cases, except for maybe a few cases which we will see subject to whether time permits, where people use open loop control such as ratio control and things like that, but in most cases we shall always be concerned with closed loop control systems. The reasons are multifarious, we will discuss them in subsequent lectures, but the point is that you see, starting with a open loop transfer function such as this, you end up with a closed loop transfer function that looks like this, which is basically nothing but the prototype of the system that we have studied, whose performance metrics we have studied. So in most cases, now notice very carefully what I am about to say, in most cases you will be required to find out the performance metric of the closed loop system. This is a very important statement, so let me write that down. We will concern ourselves with a study of closed loop system performance. We will discuss in subsequent lectures why closed loop is important and why we particularly put it in this form of closed loop, which is a unity feedback. This is a unity feedback closed loop system. Why not any other sort of feedback, but why only this unity feedback? But that is a matter to be taken up later. For now, the reason I kind of started discussing this topic is because you see, often it might so happen that your open loop transfer function, and this is very important, remember subsequently when we design controllers or wherever it is applicable, always remember this. Since we are already discussing this additional poles and zeros, you might have a transfer function that looks something like this, omega n squared upon s into s plus zeta omega n into s plus 1 by tau 1 into s plus 1 by tau 2, 1 plus s plus 1 by tau 3, something like this. Okay. So this is, let us say, your open loop transfer function. Now based on what we have discussed, it might seem to you like what you should do in this case is immediately go about chopping off poles and zeros according to that 5 sigma rule or according to the pole 0 cancellation rule. So you should immediately as if go and check what these locations of tau 1, tau 2 and tau 3, or rather 1 by tau 1, 1 by tau 2 and 1 by tau 3 are on the complex plane. So it seems like you will have one at 0 here, one at minus zeta omega n here, excuse me, one at minus 1 by tau 1 here, so one at minus 1 by tau 2 here, and let us say a 0 somewhere here at minus 1 by tau 3, right. And it might be very tempting to try and apply that 5 sigma rule here, all the pole 0 cancellation rule here, and immediately reduce this open loop transfer function to a second order transfer function and try and look at this, okay, as an approximation, and then plug this in. So let us call this the g hat, and then plug this in g hat in the closed loop, plug this g hat in the closed loop and proceed with the closed loop analysis, closed loop analysis of g hat. But what I am saying is this is something you should absolutely never do, okay, big red cross next to it, okay, you should never do this, okay. Two reasons. One, of course, you see these open loop poles and zeros have nothing directly to do with the performance of the closed loop system. Unless you put it in a particular closed loop system and find out where the closed loop poles and zeros are, you should not be able to make any qualitative statement even by looking directly at these. There are ways of doing it, we will learn those techniques later, but for now there is no reason to chop off these additional poles and zeros at this juncture from the open loop transfer function itself. So the idea is you carry these open loop transfer function additional poles and zeros through to the closed loop expression. So what you instead do is this, you put this GS here, study this particular system, okay, and then study G upon 1 plus G, which is basically GCLTF. So obviously the closed loop transfer functions poles and zeros will be somehow related to the zeros and poles of the open loop transfer function, but they are not exactly the same, they are not identical obviously, isn't it, because the zeros of 1 plus G is equal to 0, that equation will give you the closed loop poles, right. So therefore, you should not chop off poles and zeros at this stage. Instead, you look for 5 sigma rule or pole 0 cancellations in GCLTF. Very important point. Do not look for pole 0 cancellations in the open loop transfer function. Put it in the closed loop configuration. Find out the closed loop transfer function. In this case, of course, it's unity feedback, so we know it has a particular form. In subsequent lectures, we will see, even if it's not in unity feedback form, how we get it to the unity feedback form, and more importantly, why we want it to be in the unity feedback form. We'll answer those questions. For now, just take it on faith that we have this open loop transfer function which we put in the unity feedback form like this, okay. Possibly it's a higher order transfer function with additional poles and zeros apart from the second order pole and zero, yeah. So resist the temptation of cancelling out the poles and zeros at the open loop stage, put it in the closed loop configuration, check out in the closed loop transfer function whether the 5 sigma rule or the pole 0 cancellation rules hold. If they do, by all means go ahead and cancel the pole and 0 or ignore the effect of the additional pole, okay. So that is a very crucial point to remember. So while we were discussing this additional pole and 0, I thought this is an important point to remember, one where many students often err, okay. So keep that in mind. With that, we'll end today's lecture, and in the next lecture we shall talk about other types of block diagram simplification, and we'll see the beauty of this so-called block diagram reduction techniques. Thank you.